Let's look at a more interesting application here. Let's say we have a uniform magnetic field. And we can produce a uniform magnetic field a number of different ways. If you have a large coil, then at least somewhere within the interior of that coil, you can approximate the magnetic field as being uniform, or a solenoid, a coil of wire with a current running through a coil, right? So we can produce a magnetic field somehow, and let's say we have a magnetic field pointing in this direction, sort of out of the board here. And I'm going to shoot a proton into this uniform magnetic field. So I have a proton that is originally positive charge moving upward. So that's the velocity. Let me draw that again. Velocity up. Okay. And that's B. Okay, so what's the direction of the magnetic force on the proton? V cross B, thumb points that way, right? All right. What happens to the proton? How's it going to move? Okay, well, let's think about the velocity, and maybe depending on how you saw this in 205, you could also think about the momentum, right? The momentum would be in the same direction as the velocity. You have a force in this direction. You have a momentum upward. How's the momentum going to change, or how's the velocity going to change? Over a short period of time. You wait a short period of time, and what happens? Okay, the velocity is going to start swerving to the right, right? We can think of this in a number of different ways, but one way you can reason it out, if you think about change in momentum is equal to the force times the change in time, right? Or you may have seen force equal to mass times acceleration, but that's nothing more than the change in velocity per unit time, so I could write it that way as well. Mass times change in velocity is equal to force times change in time. Same thing. Well, the direction of the force is to the right, which means the change in momentum is to the right. So I have my initial momentum pointing in that direction. I have to add on to it a change in momentum to the right, and I get a new momentum pointing in that direction. So we've changed the direction of the moving proton, right? And let's say we wait a short amount of time, and now the proton is here, and it's got that direction of momentum. So we'll call that our new P initial. What's the direction of the force now? Yeah, kind of down and to the right? Because if you say V, velocity is in the same direction as momentum. V cross B, thumb points that way, perpendicular to the momentum. And so you're going to have another change in momentum over a short amount of time. And you're going to get a new momentum that way. If I keep doing this, what am I going to get? I'm going to get a circle. The force is always perpendicular to the velocity. If you have a force that's always perpendicular to the velocity, you get circular motion, right? So we can use the magnetic force to make charges move around in a circle. And we could actually calculate the radius. We'll see again how much you remember from 205. Because we can say that, again, let's look at the momentum principle, Newton's second law, whatever you want to call it. We can say that change in momentum per unit time is equal to the force, or the rate of change in momentum is equal to the force. But the momentum is always changing such that the change is perpendicular to the motion, right? And this side we can get. let's think about the force side for a second. We're looking at the force here. The magnitude of the force, or the force is going to be Q, V, cross B, right? So I have the magnitude of the charge times the magnitude of the velocity times the magnitude of the magnetic field times the sine of what angle? 90 degrees, right? 90 degrees. Sine of 90 is 1. So we're going to end up over here with just Q, magnitude V, magnitude B. What goes on this side? You remember? If you're talking about the rate of change of momentum, when the momentum is changing such that it's going around in a circle, the change of momentum is essentially perpendicular to the momentum. So you can think about the perpendicular component of dp/dt. I don't know if that rings a bell for anybody. Or if you're talking about circular motion, you can think about mass times acceleration, but now this is sometimes called the centripetal acceleration because this acceleration is perpendicular or pointing inward toward a circle. There were formulas for these things. Anybody remember them? PV, say again? mv squared over r, or someone said PV over r, right? Either way, this perpendicular component is PV over r, or we can think of this as m times the velocity squared over r, and if we plug in mv for p, we get the same thing. So what do we have on this side? We have mv squared over r. If we knew the charge, say it was a proton, for example, if we knew the magnetic field, if we knew the mass of the proton, we could solve for, if we knew the speed, we could solve for the radius. We could say that the radius is mv squared over qvb, or mv over qb. This tells us that given the radius, how big of a circle it's going to make, depends on the mass, depends on the charge, depends on the magnetic field, depends on the speed. But there are lots of applications to this idea. Anyone ever hear of a mass spec? Mass spectrometry? How does it work? Well, you want to determine what the mass of something is, what the mass of a charged particle is. You send a charged particle through with a known velocity, a known charge, into a known magnetic field. The bigger the radius, the bigger the mass. So you can determine the mass of a particle. That's one application. Okay. Another application, something called a cyclotron. Let me show you a couple of demo programs here. Here's the proton. Okay, I don't know if everybody can see this, but we have a little red particle in here in the presence of a uniform magnetic field pointing upward. I'm just doing a calculation which is similar to what you did for a program a while back where you got a proton to move, okay, to produce a magnetic field. I'm just updating the position, but I'm also updating the momentum based on the magnetic force. The green vector here is its momentum, or velocity, and that's the direction of the magnetic force. We have, let's change the perspective here, a field pointing out, velocity down, V cross B gives me a force in that direction, right? At this point, V cross B, force up. At this point, V cross B, force in. So that force is always going to be pointing in towards the perpendicular to the velocity, making it go around the circle, and that magnitude of that force stays constant. The magnitude of the velocity stays constant, but the direction changes. What if I were to try a negative charge? Okay, we're going to start on that side, and it's going to rotate in the other direction, right? We have V cross B, thumb points up, but it's a negative charge, so we flip the direction of the force. V cross B, thumb is that way, flip the direction of the force, okay? Let me show you one more thing before you go, because this is kind of fun. What if I give this a little bit of velocity in the Z, or in the Y direction, in the direction of the magnetic field? What would happen? It would make a spiral. Let's try it out. So the X and Y components are being affected by the magnetic field. The X and Y components of the velocity are being affected by the magnetic field because the force we get is perpendicular to those components. But the Z component, which is parallel to the magnetic field, essentially produces no force that is perpendicular to it because a field in the direction, or velocity in the direction of the field doesn't give us a force. So we just have this nice kind of helix spiral motion as the thing just continues with a constant velocity in the Z direction, but the X and Y components of the velocity keep getting changed by the perpendicular magnetic force. Okay? And if you've ever seen, or if you ever heard of the Aurora Borealis, there are magnetic fields near the poles of the Earth. Well, this is what happens. Charges actually get trapped in the magnetic field. Charges from cosmic rays or from the sun get trapped in the magnetic field, and they spiral in toward the Earth, and they collide with the atmosphere and give off all kind of fun light. So, okay, so we'll deal with this more on Friday.